Here's a claim that sounds like it belongs on a bumper sticker. Light has no definite existence until the moment someone looks at it. I'm a physicist. I'm not being poetic. I'm telling you that the most rigorously tested theory science has ever produced points directly to this conclusion. Stick with me, because by the time we're done, you'll understand precisely what that means, and you will never look at a lamp the same way again. Let me begin with something that genuinely bothered me for a long time. A photon, one particle of light, has absolutely zero mass. And yet, if you point a flashlight at a tiny scrap of foil dangling from a thread, that foil nudges. Light shoves it. Light has momentum. Now, you probably remember from school that momentum is mass multiplied by velocity. Zero mass, zero momentum. The foil shouldn't budge, but it does. So what's going on? Here's the answer, and it's one of the most satisfying things in all of physics. Newton's formula is perfectly fine for bowling balls and bicycles, but it's not the complete story. Einstein finished the story. Energy and momentum are entangled in a much deeper relationship than Newton realized. The full equation looks like this. Energy squared equals momentum squared times the speed of light squared, plus mass squared times the speed of light to the fourth power. Don't let that scare you. Here's what it's actually saying. For anything that has mass, some of its energy is just sitting there, locked inside that mass. That's the famous E equals mc squared portion. But a photon has no mass at all, so every bit of a photon's energy comes entirely from its momentum. A photon is pure undiluted motion. It cannot be at rest. It must move. Moving is its entire nature. And this isn't just algebra. In 1923, Arthur Compton fired X-rays at electrons and watched what happened. The X-rays scattered off those electrons and lost energy, behaving precisely as if they were tiny billiard balls smacking into the electrons and recoiling. The photon surrendered momentum to the electron, bounced back with less energy. We measured it carefully. The predictions match the data perfectly. So light carries no mass, and yet it absolutely carries momentum. It can push things. That's already pretty strange. We're just warming up. Now, you were told in school that light is a wave, and there's excellent reason to believe that. Here's the classic demonstration. Take a barrier and cut two narrow slits in it. Shine light through. If light were a stream of tiny pellets, you'd expect to see two bright patches on the wall behind, one from each slit, the way bullets would pile up. That isn't what you see. What you see instead is a whole series of alternating bright and dark stripes, like a pattern a zebra might cast if it were made of light. This is called interference. It is exclusively a wave phenomenon. When two wave crests arrive at the same spot simultaneously, they combine, and you get a brighter region. When a crest and a trough arrive together, they cancel perfectly, and you get darkness. The bright stripes are where waves reinforce each other. The dark ones are where they annihilate each other. Case closed, right? Light is a wave. But a wave in what exactly? Water waves need water. Sound waves need air. What is light actually waving through? The scientists of the 1800s had an answer ready. They invented something called the luminiferous ether, an invisible medium saturating all of space through which light rippled the way sound ripples through a room. Then people tried to detect it. They failed comprehensively. There's nothing there. Space really is empty. So what's doing the waving? In the 1860s, a Scottish physicist named James Clerk Maxwell worked something out that is, in my opinion, one of the greatest intellectual achievements in history. Electric fields and magnetic fields are not separate, independent things. They are fundamentally coupled. They generate each other. Shake an electric charge up and down. The shifting electric field conjures a magnetic field. But now that magnetic field is changing. And a changing magnetic field produces an electric field, which produces a magnetic field, which produces an electric field. The disturbance leapfrogs itself through empty space, self-sustaining, racing outward. Maxwell sat down and calculated how fast this propagating disturbance would travel. He got 300,000 kilometers per second, the exact speed of light. Light isn't a wave in any material substance. Light is a wave of the electromagnetic field itself. Two invisible fields taking turns, creating each other, rippling through the void. And that speed, 300,000 kilometers per second, is not merely a coincidence or a fact about how fast light happens to travel. Einstein showed us it's woven into the geometric fabric of space and time, which are not separate things either but unified into space-time. The speed of light is the conversion rate between them. 1 second of time is geometrically equivalent to 300,000 kilometers of space. That's why nothing can exceed it. There's no cop hiding behind a billboard. It's just the shape of reality. So, light is an electromagnetic wave. Mystery solved. We know what's waving. Except I've been setting you up because now I'm going to knock everything over. Around 1905, a young Albert Einstein was puzzling over an experiment called the photoelectric effect. You shine light on a metal surface and electrons pop out. Sensible enough, light delivers energy. Energy ejects electrons. But here's the problem that nobody could explain. Red light does absolutely nothing. You can flood a metal surface with the most intense red light imaginable. You can leave it running for a year. Not a single electron escapes. But turn on the faintest trickle of blue light, almost no light at all, and electrons immediately start flying out. Think about how deeply weird this is. If light is a wave, then a more intense wave delivers more energy. Enough red light ought to eventually kick electrons loose. But it never does, not ever, not once. Einstein's answer was radical. Light doesn't pour energy continuously onto a surface the way a wave washes up on a beach. Light delivers energy in discrete packets. We call them photons. And here is the crucial piece. The energy of each individual packet depends on the color of the light. Blue photons carry high energy. Red photons carry low energy. Let me give you a picture. Suppose you're at one of those carnival games where you try to knock a coconut off a pedestal. You could throw ping pong balls at it all afternoon, hundreds of them. That coconut won't move, but one properly thrown baseball sends it flying. Blue photons are baseballs. Red photons are ping pong balls. The number of ping pong balls is irrelevant. Each individual one simply doesn't have enough energy to do the job. So light comes in particles, quantized packets of energy. But hold on, we just demonstrated convincingly that light is a wave, the interference pattern, the stripes. Waves cancel, particles don't cancel. What on earth is happening? Here I have to be straight with you. Light is not a wave. It is not a particle. It is something else entirely, something that has no equivalent in ordinary human experience. Ask light a wave-type question, and it answers like a wave. Ask it a particle-type question, and it answers like a particle. This isn't a gap in our understanding. This is what light genuinely is. Let me show you exactly how far down this goes. We set up the two-slit experiment again, but this time we turn the light source down to its absolute minimum, so low that only one photon is traveling through the apparatus at a time. One packet of energy. It hits the detector and leaves a single dot, then another photon, another dot. One at a time, we wait for thousands of them. Now, if each photon is a particle, a little bullet, it must go through either the left slit or the right slit. So the dots should eventually cluster into two piles, one behind each slit. That's not what we get. The dots accumulate into the interference pattern. Bright bands, dark bands, the whole striped arrangement, even though we sent the photons one at a time. How does a solitary photon interfere with itself? How does it know where the dark zones are supposed to fall? Here's the answer. Sit with this. The photon does not go through the left slit. It doesn't go through the right slit. It doesn't travel through both slits simultaneously in any way your intuition can comfortably picture. It doesn't take a definite path at all. What exists is something called a probability amplitude, a mathematical wave describing where the photon might potentially be found. This amplitude propagates through both slits at once, interferes with itself the way any wave would, and then when the photon arrives at the detector, it appears at one specific location. The photon had no position before that. Asking which slit it used is like asking what face a coin is showing while it's still in the air before it lands. Not just unknown. The question has no answer yet. Now let me tell you about something I spent a great deal of time developing, which gives an even more extraordinary picture of how light moves. It's called the sum over histories, or the path integral. When a photon travels from one point to another, what route does it take? You might instinctively say the straight line, the shortest path, but that's not the full truth. The photon takes every path, all of them, simultaneously, the straight path, paths that curve gently, paths that detour wildly, paths that swing out past the moon and curve back. Every conceivable trajectory contributes. Here's the mechanism. Imagine that as the photon travels along each path, it carries a tiny clock whose hand rotates at a rate set by the photon's wavelength. To calculate the outcome at the destination, you add up all the clock hands, one per path. What do you find? Paths close to the direct route have their clock hands nearly aligned with each other. They add together coherently. But the wildly indirect paths have their clock hands scattered in every direction. They cancel each other out. So even though every path is genuinely explored, the absurd ones annihilate each other, and the sensible ones survive. Light appears to travel in straight lines, but underneath that appearance, everything is being sampled. Let me make this concrete. Consider a mirror. You were taught that the angle of reflection equals the angle of incidence. A tidy, simple rule. But the truth is that light hits every single part of that mirror at every possible angle. Most contributions cancel because the clock hands point every which way. Only the contributions near the geometric center, where nearby paths have nearly identical travel times, add up constructively. Now here's the spectacular part. If you carefully scratch away strips of the mirror at exactly the right intervals, the strips where the clock hands were pointing the wrong way, you can make light bounce off the edge of the mirror, a region where it ordinarily wouldn't go. You've made a diffraction grating. The cancellation no longer occurs. The photon doesn't follow rules of geometry. It explores everything, and the mathematics of superposition determines what actually emerges. Now let me push further. Suppose you want to catch the photon in the act of choosing a slit. You install a sensitive detector at each slit that tells you which one the photon passed through. What happens to the interference pattern? It disappears completely. Instead of stripes, you get two blobs, one behind each slit, exactly what you'd predict for ordinary particles going one way or the other. The moment you obtain information about which path was taken, the photon stops behaving like a wave and starts behaving like a particle. It commits to one slit. Interference vanishes, and this isn't because your detector is clumsy and physically disturbs the photon. You can make the measurement arbitrarily gentle. It makes no difference. Any interaction that reveals the path, however softly, eliminates the interference. There's an experiment that makes this even more head-spinning. It was proposed by the physicist John Wheeler, and it's called the delayed choice experiment. A photon passes through the two slits and heads toward the detector, but before it arrives, you decide. Either leave things alone and observe the interference pattern, or insert something that tells you which slit the photon used. The staggering detail is that you make this decision after the photon has already passed through the slits, after it has already, seemingly, done whatever it was going to do. And yet, if you choose not to ask about the path, you get interference. If you choose to ask, you get two blobs. How can your decision, made after the slits, affect what the photon did at the slits? The answer is deeply unsettling. The photon didn't do anything definite at the slits. There was no fact of the matter about its path, not even as a historical fact. The photon's history isn't determined until the experiment is complete. This isn't time travel. The future isn't rewriting the past in some mechanical sense, but it is telling you with great clarity that at the quantum level, what happened in the past depends on what you choose to measure in the present. The past is not as solid as you assumed. Let me now tell you what light is at the most fundamental level we currently understand. Picture all of space, every cubic centimeter of it, right down to the emptiest intergalactic void, saturated by an invisible entity called the electromagnetic field. This field is everywhere, always. Here's the strange part. Even when there are no photons present, even in absolute darkness, this field is never perfectly still. The reason comes from the uncertainty principle. You cannot simultaneously pin down the exact value of a field and the exact rate at which it's changing. That would be too precise. The universe forbids it. So the field perpetually shimmers with tiny, fleeting fluctuations, little ripples that arise and vanish too quickly to detect directly. We call this the quantum vacuum, and the flickering disturbances are called virtual particles. They borrow energy from nowhere for an immeasurably brief moment, then return it. You might suspect this is just a mathematical bookkeeping device. It isn't. Here's proof. Take two flat metal plates, place them in a vacuum with a gap between them smaller than a human hair. They will be pushed together by nothing, by empty space. This is the Casimir effect. The reason is this. Between the plates, only fluctuations whose wavelengths fit within the gap can exist. Longer wavelengths are excluded, so there are fewer fluctuations between the plates than outside them. That imbalance creates a pressure difference. The vacuum outside is more agitated than the vacuum inside, and it pushes the plates together. We've measured this force. It's real. Empty space exerts pressure on objects. Here's another consequence. Inside a hydrogen atom, two particular energy levels that certain calculations predict should be identical turn out to differ by a tiny but measurable amount, roughly 1 part in a million. The discrepancy exists because the electron is constantly jostled by vacuum fluctuations. The shimmer of empty space slightly perturbs its energy. This is the Lamb shift, and our theoretical predictions match the measured values to 12 decimal places. 12. The vacuum fluctuations also explain something that initially seems mysterious. Why does an excited atom spontaneously emit a photon? If the atom is sitting alone in empty space, what triggers the emission? The vacuum does. The constant agitation of the electromagnetic field gives the atom a nudge, a tiny perturbation that eventually tips it over. Without vacuum fluctuations, excited atoms might simply stay excited indefinitely. So what is a photon, really? A photon is not a little object traveling through the electromagnetic field. A photon is an excitation of the field itself, a ripple, a specific kind of vibration. When we say there's a photon somewhere, we mean the field in that region is oscillating in a particular pattern. Think about a stadium wave. People stand and sit and the wave rolls around the stadium, but not a single person travels anywhere. The wave is a moving pattern. A photon is exactly like that. It is the electromagnetic field executing a specific dance, and that dance propagates through space at 300,000 kilometers per second. When the ripple reaches your eye and strikes a molecule in your retina, it transfers its energy to an electron in that molecule. The electron leaps to a higher energy state. The ripple is extinguished. A signal travels to your brain. You see. The light arriving from a distant star began as electrons oscillating on that star's surface. Their motion set the electromagnetic field rippling. That ripple crossed space for years, centuries, sometimes billions of years. It entered your eye, set an electron dancing in your retina, and you perceived a star. You are connected to that star through an invisible ocean spanning the cosmos. Now, how do electrons push each other away? You know they repel, but they're not touching. How does one electron sense the presence of the other? In quantum electrodynamics, the electromagnetic field between the charges becomes disturbed, and these disturbances transfer momentum from one particle to the other. We describe these disturbances using the language of virtual photons, but don't picture tiny balls being lobbed back and forth. That image is misleading. It's better to think of the field itself being perturbed, and the perturbation carrying the influence. Whether the resulting force is attractive or repulsive is determined by the charges involved and worked out through the mathematics of how all those contributions interfere with each other. Opposite charges attract, like charges repel. The virtual photons don't decide anything. The interference arithmetic decides. Why does any of this matter to you? Because it reveals something important about the nature of reality. Our brains evolved to navigate a world of rocks and faces and weather. We instinctively expect solid objects with definite locations following predictable trajectories. But when we look carefully, with precise instruments and honest mathematics, we find something categorically different. Reality is made of fields and probabilities, fluctuations and patterns. The universe doesn't conform to our inherited expectations. And light, the most immediately familiar phenomenon in existence, the first thing you ever experienced, turns out to be the portal into this deeper reality. Every time you see anything, photons are arriving in your eye. These are quantum excitations of an invisible field that permeates all of space. They have no definite trajectories until they are detected. They explore every possible path. They are nudged by vacuum fluctuations shimmering in what appears to be empty space. You are not perceiving a solid, fixed, pre-existing world. You are watching the universe disclose itself to you, one quantum event at a time. When you observe a sunset, different frequencies of the electromagnetic field are triggering distinct responses in the molecular machinery of your eye. When you look at stars, you are receiving signals that have been traveling longer than our species has existed, ripples born in nuclear furnaces, crossing the void, completing their journey in your retina at this particular moment. The universe is threaded together by this invisible ocean. And here is the thing that I find most wonderful of all. We can understand it. Not completely, not yet, perhaps never entirely, but we can pose precise questions and nature gives us precise answers. We can design experiments and the results form coherent patterns. We can write down equations and they agree with measurements to 12 decimal places. Nothing requires the universe to be comprehensible, and yet it is. That fact alone fills me with something I can only honestly describe as joy. So what is light? Light is a quantum excitation of the electromagnetic field. It is not a wave in the classical sense. It is not a particle in the classical sense. It is something genuinely new, something that required entirely new mathematics and entirely new modes of reasoning to describe. Grasping it gave us lasers, computers, medical imaging, and the entire technological architecture of modern life. More than that, it revealed that reality is stranger and more beautiful than anyone before us had the tools to suspect. And we are still just getting started. Thank you for your attention. Now I want to hear from you. Out of everything we've covered today, what hit you hardest?